interpreting derivatives. And this section is very notation heavy, so we're going to be learning a lot of new unfamiliar symbols. They will become second nature with a little bit of effort. So first we're going to have a brief history lesson. Calculus was invented or discovered, depending on how you want to think about it, by two mathematicians, Leibniz and Newton, both around 1660. It was discovered independently. They didn't talk to each other. They both invented this same idea of calculus. That's Newton on the left and Leibniz on the right. So from Wikipedia, Newton claimed to have begun working on a form of calculus in 1666, but he didn't publish it until decades later. And I think Newton was kind of notorious for this. He was kind of like really into his work and didn't always get around to publishing it right away. And Leibniz began working on his ideas of calculus in 1674, published it in 1684. Meanwhile, Newton, though he explained his calculus in his book in 1687, didn't explain all of the notation and didn't explain it fully until 1693. So because of this dual invention of calculus at the same time by two different people independently, the two of them developed two completely different notations for the same ideas, and both of them are in wide use today. So we need to be able to read both of them and use both of them. Some are more conducive to solving certain kinds of problems than others, so it's really helpful to be fluent and be able to switch back and forth and use whichever one is going to be more helpful to you. So Newton's notation for the derivative of a function was to just put a little dot on top of it, and that meant the derivative of that function. So the derivative of x squared plus 7, you would write with x squared plus 7 with a little dot over it. That's not used so much in the United States, but it's very commonly used in Europe, a little dot. Leibniz used this notation dy over dx to represent a derivative, which is very intuitive because a derivative is an instantaneous rate of change, right? Which is a limit of an average rate of change. And the way we represent average rates of change are delta y over delta x. So these d's are sort of taking the place of delta as the delta gets really small, right? As the change in x gets really small. So that notation kind of matches the average rate of change notation, delta y over delta x. And then about a century later, after this was developed, a French mathematician named Lagrange, another really famous mathematician, invented the symbol f prime of x. And that's a really common one used today also. So we're mostly going to use dy dx, and we call that the Leibniz notation, and the f prime of x, which is the Lagrange notation. So it can be helpful to think of the d's in the Leibniz notation as representing a small change in, right? Like a delta, but really tiny. So dy dx means a small change in x creates a corresponding small change in y. So it's the limit as delta x goes to 0 of delta y over delta x is dy dx. So lots of notation. We may write that if f of x is x cubed, then f prime of x is 3x squared, right? You guys remember the power rule that we introduced a couple days ago? So if you take the derivative, you bring the exponent down in front, so that 3 is down in front, and you reduce the exponent by 1, so it becomes 3x squared. Okay, and that's how we would write it with the Lagrange notation, with the f prime notation. If you want to write it in Leibniz notation, you would write d of x cubed. So instead of dy dx, we're putting in the function x cubed. D of x cubed dx is 3x squared. Or d dx of x cubed. So either of those are correct. And you can think of it like following the rules of fractions, right? If I did d dx times x cubed, that would be the same as d of x cubed over dx. So that's kind of one of the pluses of Leibniz notation, is that you can kind of treat it like fractions, and it follows all those rules. And we're thinking of d dx as an operation, like do this to the function. D dx means take the derivative of the function. So 4 things that all mean the derivative would be f prime of x, d dx of f of x, dy dx, and y prime. So these are just all notations that mean the derivative of the function. So there's no new like math here. This is all just different ways of writing the same idea. It will get easy with practice, I promise. So one advantage of Leibniz notation, writing f prime of 3. Is that awkward? I don't know. I think that this one's a little awkwarder. But they're just 2 ways of writing the same thing. F prime of 3 means take the derivative, f prime of x, and plug in a 3. If you want to write that in Leibniz notation, you would write dy dx, and you put this big vertical line, which means evaluated at x equals 3. So the derivative evaluated at x equals 3. Oh, I get it. Sorry, I see what I meant now. It's a disadvantage of Leibniz notation is that this is awkward, right? F prime of 3 is nicer. Okay, little warning, you can't cancel the d's in Leibniz notation. Dy dx, you can't, it does not cancel to y over x. Dy is a single thing. That's a single unit. Dx is a single thing. Okay, and its units are y units over x units, because this is like delta y and delta x, y units over x units. In other words, the derivative has the form dependent variable units over independent variable units if you're not using y's and x's. All right, so we're going to do some interpretation of what derivatives mean in real life contexts, and we'll be switching back and forth with different notations to try to get used to them. All right, so for example, if G equals F of T, represents the cumulative number of gallons of water that have passed over a waterfall T seconds after midnight. Okay, so G is a function that counts cumulative gallons of water. How many gallons of water have passed over this waterfall? We want to find the units. Just want to know what the units are on dg dt. So yeah, so what are your units on G? Gallons. And what are your units on T? Seconds. So that's gallons per second. Shouldn't put an equal sign there. dg dt is measured in gallons per second. And other ways I could write dg dt to express the derivative of that function would be f prime of t, because g equals f of t, or g prime, or d dt of f of t. Okay, so in the context of this same example, what does g of 30 equals 120 mean? $120 gallons have passed after 30 seconds, yeah. Have passed over the waterfall. How about dg dt evaluated at t equals 30 equals 3? What does that mean? Yes, yes. At 30 seconds, 3 gallons per second is the speed of the waterfall. Right? Because remember, derivative of a function is a rate of change. So we're now measuring in gallons per second, and that's the rate of change or the speed of the waterfall. Okay, let's suppose that R equals dg dt. G is the same waterfall function above. Okay, so R is this new function, the derivative function. What are the units of dr dt? The derivative of the derivative. Right? So I'm taking dr dt, right? Dr dt. Its units are the R units over the T units, right? The units on R is gallons per second because we already figured that one out. dg dt is gallons per second. And then the units on T are seconds. So we have gallons per second or gallons per second squared. Okay. And what does that measure? Acceleration is the word that measures the rate of change of the rate of change. Yeah. So it's acceleration. Okay, so what does dr dt evaluated at 20 equals -2 mean? Yes. At 20 seconds, the speed of the waterfall is changing, is decreasing by 2 gallons per second per second. 20 seconds. Speed of the waterfall is slowing down by 2 gallons per second per second. So every second that passes, the speed is being decreased by 2 gallons per second. Questions? Yeah, sure. So we're calculating the units on the derivative of the derivative, right? So we're just, dg dt was the original derivative and it had units gallons per second. Okay, so now we have this new function that's going to represent the derivative function, and I want to take its derivative. So I'm essentially taking the derivative of the original function g. So to find the units on dr dt, I did the units on the top, right, the dr, and r is dg dt, and it has units gallons per second. So the units on the r are gallons per second, and the units on the t are seconds. So now I have gallons per second per second. And so this is measuring acceleration, which is the rate of change of the speed, the rate of change of the rate of change. So this says that the speed of the river at 20 seconds is slowing down because it's negative. All right, so I'm going to have you guys work in your groups, discuss amongst yourselves some of these problems that involve interpreting derivatives. And again, we're using different kinds of notation, going back and forth. So that hopefully is going to help you get used to what the different notations are.